Now we're going to look at Huffman coding, and we have a problem example here. Imagine you're working on compressing a large text file, e.g. a book, and to reduce its storage size. So the challenge is to represent the characters in the text with as few bits as possible. The characters appear more frequently that appear more frequently should have shorter codes, and those that appear less frequently should have longer codes. So this is the principle behind Huffman coding. Now, picture a scenario where we're going to apply here. So let's say we have a certain number of characters with their frequencies. That is how many times they appear. And let's start with that here. So let's say we have characters like A, and A, let's say A appears 10 times. 10 times. We also have a character B, and B appears 15 times. At the same time, we have a character C. C appears 30 times. And we have a character D that appears 45 times. Again, you could have more characters, but let's work with these ones. Now, the first thing that we need is we need to assign binary codes to each character so that the overall length of the encoded text is minimized. Again, that's ideally what we're achieving towards. The greedy approach to such a situation is in Huffman coding is basically to combine the two least frequent characters at each step, hence reducing the overall number of bits used. So we combine. So let's write this here. So now our greedy approach, the greedy approach here is going to be the greedy approach is to combine the combine the two least combine the two least frequent characters, and so at each step, that is, so at each step. So let's say if we're starting in the first step, we look at the two least frequent characters, and from what we have here, we can already note the least frequent characters. We have 10 A, which is appears 10 times, and we have B, which appears 15 times. So let's begin by combining the two characters with the least frequencies, that is A 10 times and B 15 times. Then we're going to create a new node representing these two characters with a combined frequency of 25. So what you're going to do, we're going to represent each of the characters as nodes, and we can do that here. So we're going to create a node, and we're going to have let's have two of them. We are also going to have a third one here. So how all this works basically is we're going to have this here is A, which appears 10 times, and we have B here, which appears 15 times. And so if we combine the two, we get 25. So that means the new node that we create here is going to be node AB, and this one basically this is going to be a combination, a total combination will be frequency of 25. So this is going to be the new node, and let's just try to connect them like that. So we have this new node that has 25. That is going to be now this basically is what we're going to have is we have this node AB that appears 25 times. We still have node C, and we still have we still have the character C and the character D, which occur 30 and 45 times, right? So again, we can represent this one's. We can also include the numbers basically, so that everything is a bit clear. So we have A here, which occurs 10 times, or rather has a frequency of 10. B, like you saw, has a frequency of 15. And now AB has a frequency, or a combined frequency here, of 25. Then now the next step we're going to do is we're going to combine the next, again, two smallest nodes, where we're going to have AB, which occurs 25 times, and we have C, which is the next one, and this occurs 30 times. So how that is going to happen basically is we're going to have C here. So okay, I should be doing this. So here we can have C on this side, and C is going to basically C has a frequency of 25, 30 times rather. So we have C that has a frequency of 30 times. Now we're combining these two. When you combine the two, we're going to create a new node that has a frequency of 55. Now that is 30 plus 25. The new node that has a frequency of 55, so let's represent that here. So we're going to have a new node that has a frequency of 55. Now the new node is going to be ABC, should be in caps, ABC, that has a frequency of 55. Now this is our second node that we've created. So this was the first one, this is the second one, and now we still have D, which has a frequency of, we still have D, which has a frequency of 45. So we're going to go ahead and actually, I had this in the opposite, so I'm just realizing that now. This 30 should be on the on the other side here. Actually, let's just move them. Okay. So 30 should be on this side. And we can go ahead and move this two as well. And this two should be here. Alright, so this now looks okay. So now the next step we're going to do is we're going to combine now A, B, C, and D. And we're going to have, now D is 45. 45 is less than 55. So that means we'll have 45 here. So here we're going to have 45, which is D. D is going to be here. And we combine these two as well to create a new node. So we combine the two. Let's just try to move this one down. Right. So we're going to have D over here, and the node that we create from here, which is going to be now a combination of all of them. So here we have D that has a frequency of, so we have D here that has a frequency of 45, and we're going to have the new node here, the new node is going to have a frequency of a combination of the two, which is going to be 100. So what have I done? Okay, let's do that again. 100. So we're going to have this combination like this. I hope all this makes sense. Right. So this is basically, once we've combined the last two nodes, we've basically created a tree with a frequency of 100. And the next step from here now is going to be to assign binary codes based on the tree structure. And the characters that are closer to the root will have shorter codes, where those that are deeper in the root are going to have longer codes. So basically what we mean by that is going to be uh, basically the time it sort of takes for us to get to the last node that we've created up here. So how we're going to assign those is, so we have okay, so we'll represent them by zeros and ones. Now, what you need to understand as well here is that when you are representing these characters in memory, each character basically takes 8 bits. 8 bits should be in lowercase. So each character takes eight bits, right? So now, what you're going to do? Let's first of all assign the frequencies basically, or the codes to this. So we can give this 0. This should be 1, and we do the same here. 0, 1, 0, and 1, like this. So these are the codes that we've assigned the two. So how at the end of the day, if we want to sort of send all this over a network, there's going to be basically what you're doing here is we're trying to reduce the size, right? Once we are sending this on top of of our network, we try and calculate the original size. Basically it's going to be 8, because each takes 8 bits. And then we're going to multiply 8 by, so we have 10. All this was 100, so 8 by 100, which means it had a total of 8 bits. This was a total of 8 bits. It was the basically the size if we were to send such maybe such text or information over a network. But after applying Huffman coding and basically reducing all this, how this is going to occur basically in terms of now, after the encoding the size and reducing it, it's going to reduce to, so we're going to look at a few things. First of all, the frequency of these characters, then the codes that we assign the characters, and the size that results from that basically. So for example, we have we're going to have, let's say we have b here, and b is b. So for b to get to 100 here, its code would be 101, and the size of b resulting from that is going to be the frequency of b, which is going to be, the frequency of b here is 15, multiplied by the number of steps that is took in this case, which is going to be 3. So let's calculate that here. So for b, it's going to be, let's do this. Yeah, so for b it's going to be 15 multiplied 15 15 multiplied by 3, and this gives us 45. And let's go to a as well. A is going to take 3 steps also. So for a is 001 is going to be its code, and so it's going to be 10 times 3. So it'll be 10 times 3, and the total size there is going to be, it's going to be 30. Now let's move on to c. If we try to send C now from C from C to the combined, so let's call this one A B C D. From C to that, it's going to be, its code will be 1 1, but it's 2 levels, so it's going to be 30 multiplied by 2. So 30 multiplied by 2 should be multiplication. Now that would be 60, right? And let's move to D. D takes only 1 step. As you can see here, its code is also 0. So D is going to be 45 times 1. So 45 times 1, and that gives us 45. If we do total, the total bits here is going to be, so 90 plus 90, that's going to be 180. Right, so 180, it's going to be 180 bits in terms of the size the size that we'll be sending. And that is basically it. And in terms of the characters, we're only sending 4 characters. So each of them 8 bits. 8 times 4 is going to be, so just 8 times 4 is 32. So 8 multiplied by 4, that is going to be 32 bits, 32 bits each. And then the kind of the steps that it basically takes to get us through everything. And if you also add the total frequency was 100, so that would also be 100 bits. So the total frequency will be 100 bits. Now if you combine the entire size that we are sending over a network here, so this is a full total that we are sending over the network. It's going to be 180 plus 32 plus 100. That becomes 280 plus 32. That becomes 312. 312 bits. As you can see, this is a reduced size or rather as compared to the original size that was to be sent, which is 800 bits, and now we're sending 312 bits after doing the encoding. And that is basically what Huffman coding is. There are a number of ways that we can represent it, but this is a greedy approach that we can apply across. I hope all this makes sense. If there's a question, feel free to ask in the question section in the comments, and I'll be happy to answer it.